Hello, everyone. Good afternoon. Can everybody hear me okay? Ah, hello. Hello to you too. Okay, good. So I guess in a minute or so, let's wait for everyone else to come. I think only have 10 students today. So we're still waiting a little bit, maybe a minute or so. All right. Can everyone see the slides? Okay. I think so. Okay, thank you very much. Thanks. Okay, maybe I'll backtrack a little bit where we stopped last time and start from here while we wait for everyone else to come. And so I guess last lecture we had a look at Gauss-Newton method, Newton's method, and also conjugate gradient method. And also previously you had a look with Professor Feng Liu, the steepest descent method, golden section, and parabolic approximations and such, right? So in this lecture, we will look at some examples that where this is used, for example, in one of the MRI groups at University of Queensland, this is used, for example, to optimize different hardware components. And of course, if you have interest to apply for PhD positions within the group with Professor Feng Liu, he might have some positions open. You can check with him. This might be of interest to some students. Maybe there's some scholarships available, who knows, right? So you can check. But otherwise, I think last time I mentioned that this system, which we use as an example to illustrate how you can actually optimize using these algorithms, some of the components such as superconductors, gradient coils, RF coils, different sets of components inside the system. Pretty much the whole system contains a huge amount of subcomponents and also software and algorithms which need optimizations. And this is where you find linear algebra and optimization algorithms. Very, very useful, right? So we discussed a little bit about gradient coils, the three sets in that example case. And you can see here how the winding patterns are very complicated. Normally, the way you optimize this structure is using some sort of stream function as optimization function. And you have a current distribution, which is a current density profile on the surface of a cylinder. And then you discretize this into current carrying loops at the end, which creates a pattern. Then you build it, you construct this structure, and you have to then cool it. I'll show you later on how it looks like in when it's manufactured. Often, for example, you might have, in this case example, secondary windings. This is where we stopped last time in the lecture. The secondary windings are used to shield the field from leaking outside the region. So we want only the field to be in the middle of the region, uniform. By uniform, I mean that the magnetic field produced by this structure along, say, in this case, y direction. So this is a y coil along this way, is very uniform gradient. So magnetic field varies in space linearly. So it's very high here and then decreases. This is only one cross section. Actually, this is a spherical volume. So it's actually a volume region where this is happening. And this has to be therefore designed to operate in a volume. If you take derivative of this function, you would get something called uniform gradient G. So G is dB Z over dy. So this will be that kind of gradient which is designed in the center of the imaging region where you want to scan the patient. Here is another example of a more efficient coil structure, also obtained by, let's say, conjugate gradient method optimization, for example. And you can obtain the stream, well, the current distributions, and then discretize into current loops and such. But what's unique about this is that you have now optimized to have a structure conformal to the head geometry, and it's also a smaller volume of space consumed. And this is a very efficient structure which can take less current, less power to operate, produces a very strong field locally, etc. So it's very efficient to have a localized gradient set as such for head imaging. And you can see here how it's optimized, let's say in MATLAB or like could be Python. You can actually design it to have a uniform region. And this red region here denotes the uniformity section of that space. This is a cross-section at three-dimensional volume. And these are the loops which are carrying the current out of the plane and inside the plane as X, right? And these are just fringe fields. Fringe fields leak outside. We want to minimize those so they don't come to the superconductors. They can quench, heat them up, and the superconducting will stop and then cause, like the helium to vent outside at high pressure, and that's not good. That's actually an accident, So we have to prevent that from happening by shielding this system by secondary windings. This is an example of a also designed using optimization algorithms, and having objective functions, as we studied so far in the last lecture, to optimize for breast imaging, because, as you know, mammography is not always great because of radiations for breast, but MRI does not have radiation. It's using magnetic fields, so it's not ionizing. It does not accumulate radiation dose in the tissue. So it's very healthy compared to, let's say, CT and other techniques. And but also MRI has its own, health concerns, which of course, you have to look at current strengths, field strength, etc. There's some limits internationally imposed, but it's not as bad as, say, X-rays, for example, or anything radiation-based. Here we have this structure conformal for the breast imaging, and the patient would lie flat on the bed, and then normally the breast will go inside that region, scan for lesions. Sometimes the issue with it's a big problem. There's, I think, 1 in 7 women experience breast cancer, which is very big problem. And also men have prostate cancer, so you can also design some structures for the prostate imaging. But usually this is what's done in MRI industry these days as well, to get a better image, Here's one example of green coil, which I showed you previously with those current carrying loops. You see here there's a water pipes through the structure. These are carrying water to actually remove the heat. So when you design this structure, you have to take into account temperature, Lorentz forces, because if you imagine when the power sequences for imaging are used in MRI, these currents are passed through these loops as a trapezoidal pulse, almost like a square pulse. And they create very strong currents, like up to a few hundred amperes. They have to be pulsed at high voltages, maybe even kilovolts, and it has a lot of power consumed, right? So these currents are very high. They're flowing through a static field produced by a superconducting magnet, and if you have a charge like electrons or holes flowing through a magnetic field, using right-hand rule, you will realize there will be a force acting upon those charges. That force, the Lorentz force, will be very strong, and it will twist and torque the structure every time you go positive and negative in the pulse. So it will be experiencing acoustic vibrations, therefore, at low frequencies, and you will hear the pulsing like a boom, boom, boom. This is what you hear in MRI in hospital. If you do MRI, you will hear acoustic noise produced by Lorentz forces when these grains are twisted due to very strong forces. And you have to, of course, minimize those forces You have to make sure you can optimize the current distribution, optimize the temperature flow, using temperature calculations, like in simulation tools. And you have to check for outside fields to be minimal, inside fields to be uniform. And you can imagine it's a lot of things to optimize in one go. And so you have to have a very large objective function, which takes into account everything which you are trying to achieve. And there's a lot of engineering going on here. And of course, eddy currents are problems. So when these are paused, eddy currents are very large, and you have to minimize those eddy currents as well, both in space and in time. So this is a real world engineering problem, which you have to use all this knowledge of matrices, knowledge of linear algebra, knowledge of optimization tools. Here is another example for RF radio frequency antennas. Let's say if the field strength is 1 Tesla, you would typically have about 42.58 megahertz frequency. If you have, let's say, 1.5 Tesla, it's about 65 megahertz. And then 3 Tesla, 128 megahertz. So it scales linearly with frequency. So these are resonant structures which pick up the signal from the tissue, and they have to be optimized for transmission and reception. So you transmit the RF pulse to excite the tissue, then you receive that signal from the tissue to get image. And these structures are usually antennas, RF antennas, just like you use for radio stations, very close to those frequencies, but they actually are in a shielded room, so in a Faraday cage inside the MRI's room, and they don't escape outside the room, so they don't interfere with radio stations outside the, and so you have to also design the RF room as well. Imagine, like, you have to also design that and optimize it. So this transmit receive coil, this one here is a transceiver, so it does both functions, not separately. It does both transmission and reception. Is designed, as you can see, using some sort of like a stream functions or some sort of sophisticated maths, having objective function optimized using conjugate gradient method or some sort of Newton's method or similar. So you can do that, right? And it creates a better field profile in the imaging region. This one here may be conventional one, maybe creates dark and bright regions. So clinicians might complain. Then you use this structure, you optimize it to be something novel, something new, better, and you get a really nice image, right? So this is also done in megahertz ranges. So here's one example from, this is the last example for this lecture, from past exam. This example was a little bit difficult. Many students, as I was, I think, as I figured out from past lectures, that Professor Feng Liu said, many people said that this was a difficult question. So we might not have such questions anymore in the final exams. It's up to Feng Liu, Professor Feng Liu, but here I'll just show you what, as an example, so for you to just know that just as example, not to think of it as a final exam question, basically. So let's say we have a Z gradient coil, and we want to optimize in the center certain magnetic field to be uniform, or gradient to be uniform at these points P1 to PM, and the many points. So if you have a structure like this, you have R radial component and Z longitudinal component, and you have all these loops with radius A and current I flowing through each, and they all have same current, let's assume, right? Maybe different direction here, maybe opposite here, but they are different positions. So this is a position Z1, Z2 up to Zn. So they're different positions along Z direction, and they're not varying in R. They're always same A, same radius. And you have to now optimize these positions Z1 to Zn such that this field in the center is always uniform in this region. We remove the phi component in this case because it's axially symmetric. So we can assume this to be a two-dimensional axisymmetric problem. And then we can define a function which computes the gradient at one point in ZR. So this is a coordinate system. This is just for one point, and we have a gradient. And it's some sort of function which is like a conceptual function. It's not actually computationally going to work, but it's just for the exam question that this was the conceptual function, and this was saying that it's a coefficient k, which is a constant, n number of turns, and f is non-linear function. And we have here, for example, the field point here G at ZR, and we have also position ZS of the coils. And we want to actually figure out how to define the objective function, and such that the gradient, computed gradient, in those points in the center, is away from the target gradient, which we want, no more than 5% deviation. So this was the constraint on that function, and we want to express it somehow. So the solution would be, okay, first the question was to model the above optimization problems to set up objective function and constraints, and then to do some sort of suggestions how to optimize this, what algorithm to use. So this would be one example of objective functions which you can write as an answer, let's say. This would be to minimize, of course, the sum of squares of the point that we're computing, gradient point GM, minus whatever the target is, maybe like, I don't know, 30 millipascals per meter or something, some constant. And we have to minimize that. And this would be the answer, right? This would be the answer. And the rest of it is not really defined in the previous question, but if you write it down, it would not be wrong. It would be still correct. And this is showing you understanding of the problem and reality. This is the real world situation, let's say. And let's say if you wrote something as well, that the magnetic field outside the region at points P1 to PM, which is leaking outside, has to be minimized as well. We want this to be 0, so we're minimizing it. And we have some coefficient W as a weighting factor for this to work alongside this here. So we have just a scaling factor for this objective function subcomponent to work. And it's just some inductance. It's just saying that, well, I want to minimize inductance or resistance to something because I don't want eddy currents to be strong or to consume too much power, because this inductance will take long time to charge. You know, like once you pass the current, inductance will take long time to charge up the field inside, and it will slow down the pulse. So here we have these constraints from minus Z max over 2 to Z max over 2. So this is just something like this you write down, and this would be the answer for your objective function for this real world problem, right? And here's an example how to solve it. This would be, let's say, using the conjugate gradient method, as we discussed in the last lecture, initial guess, direction, and along the line search, and also the distance. You do that, and you do that beta parameter compensation, just like before we discussed last lecture. And this would be one answer, how to solve it. And this is something you describe. You say, this is how I would do it. And you repeat the procedure to some degree as close as possible as you can. And that would be the answer. This was a difficult question to some students because I think it was trying to convert that knowledge to reality, you know. So let me just step out of here. Why is this not okay? Here we go. All right. So now next set of lecture notes for next half an hour. I have to introduce linear least squares. So this would be basically based on whatever Gauss came up with in early 1800s. And there was, for example, the way it came about, the linear least squares at the time, was when astronomers were looking for Ceres, which was one of the asteroid objects in the asteroid belt between Mars and Jupiter. And it was going behind the sun, and they were tracking it for 40 days, but then they couldn't figure out certain mathematics. So they used Gauss's calculations of linear least squares, and they came up with the solutions at the time to discover Ceres. And that at the time, Gauss was only 24 years old, which is quite impressive. I think those days, Einstein was probably 26 when he got Nobel Prize, and everyone else in those days, old times, were always smarter when they were younger, it seems, right? Always, but maybe not so. We still have smart people these days. But I guess this Ceres, I think it's a small object now called dwarf planet, probably around 900 kilometers in diameter, just like distance between Brisbane and Sydney. That's the size approximately, not too big, but it's sitting asteroid belt, and it's a dwarf planet since 2006, I think. So, and yes, so this guy, Gauss, came, it's a very popular scientist, mathematician came up with linear least squares and contributions to non-linear least squares, etc. So it's very good. So how do we do linear least squares? Let's say we have some measurement, just like last time with the non-linear least squares. Now we're dealing with some sort of linear functions. We have a line fitting or regression fit through the data points, and we want to have a closest fit, right, of this line through those data points. We have data points xi, yi, so x1, y1, x2, y2, etc. And we have a model function y equals ax plus b. So gradient of that line is a, and intercept of the y-axis is b, and we feed these points y and x in here, and we want to minimize this function relative to data points. So we are looking, again, if you remember, what we always want to do is we look at the error or the residual, the distance between this line and this point, and then this line and this point, and we square them and add them up together to actually get some sort of objective number to minimize, right? And this was the procedure with linear least squares, and same deal is here happening with linear functions. And so this is what I just said, that we have sum of squares or L2 norm. So we have that model function ax plus b, which we are trying to fit the data to, and we calculate the residual, which is our measurement y. So it's the y value minus that value from our model function, and we square it. We want to remove any negative and positive differences. So we want to make everything positive in that sense, and we sum it up to get one value, and that would be this error function that we are trying to minimize. So the objective is to always minimize that error, right? And to find the best fit. Of course, if you look at this data, we can't fit this through perfectly to every point, but we're trying to find a minimum error sum or minimum sum of squares, and therefore to find the best fit, and not the ideal fit, but best fit, closest possible we can get. And so normally what we do, of course, is the general solution would be to always have a function to be minimized. So in this case, we have sum of squares to be minimized. This is the first step, of course. And second step is, once we have something to minimize, let's say you have some sort of function x squared plus 2x plus 1, like x squared plus 2x plus 1, and you want to minimize it, you want to find the minimum, right? So you take the partial derivative in respect to x, or derivative in respect to x, which happens to be just 2x plus 2, and you set it equal to 0. So 2x plus 2 equal to 0, and then solve it, x equals minus 1. So you find the minimum like that, right? So you take the derivative and you set equal to 0. That's the procedure always, right? To find the minimum or to minimize. And then we have, of course, take some sort of special function form of it later on, as we will see. So, okay, so the general form for such least square fitting or least square solution is this one here, in terms of these basis functions. This is how we mathematically and generally express such a problem mathematically. So we have af of x at I plus bg, another function g of x plus ch of x. So this is generic formula, something mathematicians would do theoretically to express. And here, how would you think of it? Let's say this part here is a. So this part here is a. So, and therefore f of x is just 1. Or I can, let me write here, use annotation tool to actually do a little bit sketching. So this one here, you can think of it as being x to the power of 0, which is equal to 1, right? This one here, you can say this is x. This basis function is, say, x. This one here, bx, right? And this one here is ch something else. So this could be, if you have more terms like this one here, another term, this would be x squared. So this is x squared, this is x to the 1, x to the 0, x to the 0, right? So these are basis functions. And now we're having a a square function. Sometimes the reason you would want to have this polynomial for fitting, it's not just line, it could be higher order fitting. It could be, for example, because let's say you have data points, and sometimes the data points could be like this, right? But then they could go down, so like this. So if you're trying to fit a line through it, it would not fit these ones. But if you're fitting a square function, it might find a better solution. So you're having a higher order expression. So this is sometimes depending on the polynomial order. So in this case, this would be the idea behind it. So of this generic form. So let me just remove the drawings. Okay, so if we go to next slide. Okay, we got 20 minutes. Okay, so we have here, in this case, as we said, we want to take the derivative or the gradient of the objective function, which is sum of squares. This is a sum of squares, which we now expressed, right? So y minus a f of x minus b g of x. So all we did is substitute this model function in here, and we're getting this expression now for that sum of squares. Very simple. But we want to take the derivative of this function and set it equal to 0, right? This is what we minimize it with, to take the partial derivative in respect to each parameter. In this case, the unknown a. So we're trying to solve for a. We already have, let's say, this one here. This could be just x to the 0, x to the 1, etc. We can feed those data points. We know the measurement x, right? We know the measurement also y. So we have x and y, but we do not know a and b and c and d, etc. So other values. So those model coefficients we need to actually solve for. This is why we take the partial derivative in terms of these coefficients a, b, etc., and it's equal to 0. So if you take the partial derivative, this is what it becomes. So the derivation of these square brackets to the power of 2 from high school maths, you remember it's just taking the derivative in respect to in the brackets in terms of whatever a is, and this happens to be this scalar looking factor here. You factor it out in front so that this becomes f of x, and then you divide the inside the brackets just like in high school maths, right? And you have a 2 exponent which becomes coefficient 2 in front, and this becomes n minus 1. So this is n minus 1 here. So this is 1, right? Here I have exponent 1, and there you go. So this is now derived. You have a derivative, or you have done differentiation now, and in terms of a, right? And it's equal to 0. Here you go, equal to 0. Now the next step is we can now separate those summation terms and factor out all the coefficients a, b, etc. So if you factor out a in front and you bring f of x and f of x together, you get the sum of f of x's here. You get sum of f of x times g of x here, and you bring the y, this factor here, to the other side. So if you do a little bit of maths and rearranging, this is the form you can actually derive from here, in 1 or 2 steps. And the 2 vanishes because we can bring it to the other side and divides by 0, so it's still 0. So this goes away, and the negative signs you can account for this expression then is the final expression. So once you check on your paper, you'll see this is what you get. So you can also see it from here. Now, also for the other coefficient b, we do the same thing, but now we have a g of x basis function here. So we bring it out, same thing, but now we have g here instead of f, and now we have the g, f, etc. Right? Same thing, exactly as before, same procedure, and you get something in terms of g now. Everything is multiplied by g, and you have the similar form here, but now here is a, b, etc. So now you have those 2 done, and you can do more of them, of course, but we don't have to. We see the syntax, we can see how it's going, and we can now write it in matrix form. So if I just step out of this thing, and I guess I can, yeah. So just have a look at this one here. Okay, maybe this one here. Sorry, I'm trying to. Okay, maybe you can't see this well. Okay, I'm just trying to show you. Okay, so the first line in the matrix, is just this part, f of x times f of x, and then times a. So you have a here, then this term here, which is this term here, times b, etc. The second line is then this term here times a, and then this term here, which is here, times b, etc. So now we are rewriting this set of equations in a matrix format, which is now giving the same thing if you multiply out, right? And this one's here on the right side, these values are just rewritten here in a vector form. So what we now have is this matrix equation system, A times X equal B, which is a matrix system, right? So we have a n by m matrix, and we have a vector, another vector here. And we can also alternatively, but I guess we don't have to do that. It's just to see what it looks like if we have this written in this format, like we have a vector g, f of x, g of x, etc. And we take the transpose of it and multiply with the transpose, this would populate a matrix. So this times this would be a matrix. But if you had, remember previously we had transpose on the other side or in front. And in that case, it multiplies to be a sum of squares, kind of, if you remember. Transpose times the vector. Vector transpose times the vector is equal to some sort of like it reduces the size of the vector down to probably one component only, if I just numbers inside. But here we have a matrix if we multiply it this way. So vector times transpose of the vector is a matrix. And then we have this one here, and the final one, we can factor out the summation yi in front and get a vector from the other variable. So that this would be another form to write. But let's focus on this form here. So this form here is what we want to look at, ax equal to b, which we are used to. And then this is what it is, right? So we have a times x equal to b. This is an n by m matrix, where the number of rows corresponds to number of measurements in the data set. Let's say we have 100 measurements, like of x and y, you would have 100 lines, 100 rows. And the number of basis functions you have, let's say you have x to the 0, x to the 1, x to the 2, maybe 3 of them, you might have only 3 rows, let's say. Sorry, I mean 3 columns, 1, 2, 3 columns. So this becomes 100 by 3 matrix. It's a rectangular matrix, which is longer vertically. And then you have m by 1 vector here and n by 1 vector here. These are measurements, right? And these are the coefficients A, B, C, D we want to compute from our problem model function. And as you can see now, we have only m. Let's say we have 3 unknowns, but we have, let's say, 100 equations. So there is no solution to fit 3 unknowns into 100 equations. We have to somehow make a best fit, right? And to be able to actually invert this matrix A, the problem is that because it's rectangular, it's not square, it's hard to find the inverse. It's not going to work. So it has to be square to be invertible. And it has to be, of course, not singular, and it has to have independent columns. And all those matrix aspects need to be fulfilled, those requirements for a matrix to be inverted. In this case, we have to do something about the problem. So we're going to discuss this next. So we can actually, one way to solve this would be, of course, to just write equations down as normal equations. And this could be done by basic algebra, but it's inefficient. It's also, takes time to compute. You can do QR factorization by decomposing the matrix, as you will study in coming lectures in the future, in the next few weeks. You can do a singular value decomposition. You can do some sort of conjugate gradient solution, etc. And there's many ways to solve it, which we will study in the coming weeks. But one of the ways which I will show here, which is very neat and very useful and also very popular in statistics. Statistics uses this a lot. And let's say if this was the problem n by m, and let me write a little bit down here. So you have n by m matrix here. And if you multiply both sides here. Look at this form here. So you have AX equal to B, but if you multiply A transpose on the left side and A transpose on the right side, you're not changing the form, but you're introducing something, introducing some simplification. Now A transpose A, where A is n by m, so this would be A transpose A. I'll just give you one example. Let's say if A was, let's say A was something like 100 by 3 matrix, right? 100 by 3, then A transpose A would be, this would be 3 by 100. Okay, I'm trying to write by mouse. And the other one would be 100 by 3. Okay, so then this is n by m, by the way. Sorry, m by n in this case, and this would be n by m, the A matrix. So this one's here cancel, and you get m by m. So you get 3 by 3 in this case. So you get A transpose T in this example case, as I'm just using some numbers, will become 3 by 3. So it's significantly reduced from 100 to 3 to only 3 by 3. And on the right side, you would have A transpose B. This would be, let's say this is still 100 by 1. I'll write it down here, 100 by 1. This is the B vector. And the other A transpose, which is this one here, is basically also, what is it? 3 by 100, right? So effectively, we cancel these two, we get 3 by 1. So A transpose T times B is 3 by 1. So also reduced. So you're getting a much smaller system of equations. And originally, this matrix was over-determined or over-constrained. Now it has been reduced a little bit. And this is called, if we now have this formulation, now we have a square matrix, 3 by 3, which is square. And hopefully it's invertible. And if it happens to be invertible, we can find the inverse. So now we can actually compute the inverse. So basically, then X becomes equal to this A transpose A inverse times A transpose T B on that side. So this is the right side. We bring this term here to the right side, and this becomes an inverse. Very simple. So X, so for X here, X equal this matrix here, this composite matrix on the right side becomes inverse. So you have a -1, and there you solve it. So this is the general form, this one here. This is important way to look at it, right? So, but this thing has to be not singular, because if it's singular, sometimes it can happen, not always, which means it does not have a determinant. Determinant equal, sorry, I mean determinant is equal to 0. So if determinant equal to 0, if you remember, for a 2 by 2 matrix, you would have determinant is A times D minus B times C, right? And if determinant is 0, you would have 1 over 0, which is infinity. So this is not possible. There's no solution then. So this must not be singular, but sometimes it can happen. But so one has to be careful, of course, to look at this. And maybe something else needs to be done instead. Maybe this doesn't work. But this is the general way, using the pseudo-inverse, what's called of A. And this is the formulation. And very useful, very frequently used. Also in MATLAB, you can do PINV, P-I-N-V. I think if I remember correctly, it's pseudo-inverse and of a matrix. So you can PINV A and you get a solution. So next slide. We have 10 minutes. I'm not sure how good we're doing with time. So let's say sometimes it can happen that you have some sort of noise in the system, in the data measurements. You have the measurements Y and X, right? And you have lots of noise, and you have some sort of issues with some sort of measurements, some, not all, but some measurements. And you know which measurements those are. So what you can do is you can provide a sort of scaling factor that can compensate for those measurements. So let's say if some measurements are not so good, you maybe want to use scaling factor like 0.1 or 0.2. But if the measurements are good, you want to use maybe 1. So you're weighting it by 1. So you have 100% weighting. You give it more power. But if you don't want to have some measurements, you want to reduce them a little bit, you just multiply maybe by 0.3 or something, like something smaller. So you might have something like this, like a W or matrix which has diagonal of those coefficients, W1 to Wn, and each of these will multiply by vector B. Let's say you have this one, W times B. So this will be W1 times whatever the first entry is in B. So that could be that measurement Y1, and then W2 times Y2, etc. So now you're multiplying element-wise. The other ones are 0. Of course, you're not multiplying anything there in this context. So you're just using individual multiplication for each value you have in the measurements. And you do this for both sides, of course. You introduce this W matrix on both sides so that you can actually make it equal in terms of mathematical equality. And therefore, you put normal here between these two matrices, and this is the form. So this is something you can also do very conveniently on a computer or by hand even sometimes, but normally by computer, of course, because you're dealing with engine problems which are a little bit larger scale sometimes. You wouldn't do by hand everything, of course. It would be not suitable. But so yeah, this would be the way to do this. And it's called weighted fitting. Yeah, so weighted least squares. So let's say we have a problem which contains some sort of complicated formulation like exponential. So we have some sort of a, e, b to the x, e to the power b to the x, bx, I'm sorry, bx. So if we take a logarithm on both sides, log of y and log of ae bx, you would eventually find that this side is log y and the other side becomes just log a plus bx. So this falls away, the exponential form falls away by logging, mathematically equivalent. So if you look at those math tables, so if you remember how to do these logarithms, so this is what you get. So if you know it by taking the logarithm, the left side is log y, but the right side has a form of a linear equation now. So we have here a value, call this a star. So this log a, let's call this a star. So a star plus bx is nothing more than a line equation where we have a star as intercept, y-intercept, b is the line gradient, and x is the variable, right? So you're getting a line equation. So now we have a line equation. You can now do linear least squares and fitting, etc. And once you have done your line fitting and all that, let's say you can get solutions for a star and b. You find those unknowns, and once you get that solved and everything, then you can recover what is a. So you can go back and find a again, because we know a star equals log a. Therefore, a must be equal to e to the a star. So to recover a at the end of the solution, you just write exp a star, and you get your answer in terms of a and in terms of b. So sometimes you can use, this would be like an interesting way to linearize it and to solve it. And it's a little trick you can use sometimes if you have a problem of that nature. Let's have a look at an example before we finish this lecture. So let's say we have 3 mountains, U, Y, and Z, and we measured that those heights of those mountains using an instrument, optical instrument or something, like a laser beam or something. And we measured from some location from one side, and we measured that U is 2,474 meters, Y is 3,882 meters, and Z is 4,834 meters. So this is our measurements. But then we go from a different location and we say, okay, but from location U, from the mountaintop U, Y looks 1,422 meters taller than U. So Y is taller than U by 422 meters. And z looks to, and also z looks taller by 2354 meters compared to u. So from u, these two, y and z, look taller by this much. And also from y, if I go to the top of mountain y, z looks taller than y by 950 meters. So, but if you look at this, so basically you will know that, let's say this one plus this one, it's not going to equal this number. It's about 4 meters off or something, I think. So you're having a little bit of error in measurements, depending on how you, from which location you measure. You're having multiple views, right? View, from this view, from that view, and you're having different measurement data sets, which contain some error. They're not coming up to be exactly true. So you have to solve this somehow. So to do that, we can write a metric system as this, and we can say, okay, so I can write the first equation. The first equation says that u equals 2474. So I have here 1 times u equal 2472, 0 times y equals this. So therefore, everything else is not being considered. So we have here y, u equals this one, right? So 1 times u this, 0 times y is that, etc. Now the second equation is that y equals 3882. So okay, so we have here 0 times u, 1 times y. So we have y equal to 3882. So we have a second equation. And then, and a third equation is that z equals 4834. So this is the third equation. That other coefficients are all 0. So if you write this down as equations, basically this will be 1 times u plus 0 times y plus etc. So this is what you get those values. Now let's have a look at the other three from other measurements. We said that from u, y looks taller. So we therefore minus u plus y, effective minus u, so minus 1 times u plus 1 times y equals 1422, this fourth row. So it's effectively that y minus u is positive 1422. So we know that y is taller. So we're taking difference that y minus u is this much. And also z, here 1 times z minus u is 2354 as here. And the last one is that z minus y is 950. So here z looks taller than y. So here z time minus y is 950. We have the rectangular matrix here, and it's over-determined, it's over-constrained, it's got more equations than unknowns. It's a 6 by 3. So if you look at those spaces in algebra, you have to spend this space to this dimension of 3, which is not possible. You have to fill it somehow. So the one way to do so is, as we introduced before, is to take A transpose A times x equal A transpose B. So if we take transpose of this, so this would be, I think, something like first row would be 0, 0, 1, 0, 1, 1, and then I think the other one would be 0, 1, 0, 1, 0, minus 1. And then, so we have two matrices. I'll show you. I won't probably be able to draw it here. So you have the transpose, which is like this. It's a 3 by 6 matrix times the 6 by 3 matrix. And effectively, the result would be 3 by 3 matrix, effectively. And this one here would be also 3 by 1 in the end, if you multiply this 6 by 1, 3 by 6, which is this is A transpose A. And you can have a look how to take the transpose. You have to take the rows. So this, the first row would be this, second row would be this one, and then third row would be that one. And it's actually flipped, it's pivoted, kind of, it's pivoted around this point. So you can have a look how to do that on a small matrix. I don't have maybe much time here to explain now, but okay, so this would be that 6 by 1 vector B, right? So this would be the AT. And this becomes effectively result is AT is then 3 by 3, and this one here is 3 by 1. The final result. I'm just showing the final result would be smaller once you multiply out. And then you can solve it by taking the inverse of 3 by 3 matrix inverse. You can also look up how to get the inverse of that one, or you can have 3 equations with 3 unknowns and solve it like you did in high school, like without using matrices. You can do it by hand, just using basic algebra. By substitution, you multiply some rows by certain factor to make it equal to other row, and you subtract one line to the other. There's many ways to do so, like in high school in year 11 and 12, maybe even 10, I think it was studied. Okay, so this was that. Anything else here? Did I finish the slides? Or yeah, that's it. So I think there's more about these linear least squares in the matrix optimization toolbox, where you can actually play around numerically. I'm pretty sure that the tutorial this week or next week will be about some of those questions regarding MATLAB numerical programming. So it's good for you to actually understand what's going on. So when you use the computer and MATLAB toolboxes, that you understand what's happening and what's going on. So yeah, I think I'm going to stop here. We are over with time, and you have a new lecture, maybe, I'm not sure. It's already 5 p.m. But thank you so much for your patience and coming today. If you have any questions of any sort, let me know. I'll try to answer. And yeah, so I hope you have a good week, everyone. So thanks. Oh, thank you very much. Sure. And everyone as well. Thanks, guys. Thank you, everyone. Yeah, have a nice week, guys. Okay, see you. I'm going to go now, so no questions, I guess. All right.